In computer science, some books are just legends. This one is called The Dragon Book, and it's a classic guide to how software gets made. But hidden inside all those technical pages is this really beautiful idea about solving problems, an idea that works for way more than just code. It really all starts with a pretty simple question. When we write code, we're using a language that's made for humans to read, but the machine itself, it speaks a completely different language. So how does a computer actually get what we're telling it to do? That act of translation, that's the puzzle we're going to look at today. So let's take a look at this one little line of code. I mean, it seems totally straightforward, right? Just some basic math. But for a compiler, that's the program that translates our code for the machine, this simple line is actually hiding a really important choice. And that choice is what we can call the translator's puzzle. See, the thing is, there's not just one way to translate that line of code into machine language. There are actually a ton of different ways, a bunch of different paths the computer could take to get the exact same answer. And not all of those paths are created equal. And this slide really shows you what I'm talking about. On the left, you've got a clumsy path. It's inefficient, it's loading and storing things it doesn't need to. It takes 9 steps to get the job done. But the path on the right, it's elegant. It gets the same result in just 5 steps. So the real question is, how does a compiler figure out how to choose the elegant path over the clumsy one, automatically, every single time? And believe me, this isn't just some minor academic detail. The stakes are actually huge. As the Dragon Book itself puts it, a naive or clumsy translation can lead to code that is unacceptably inefficient. And that means slower apps, wasted battery life, and just a worse experience for all of us. Finding that elegant path is absolutely crucial. So, how does the compiler solve this puzzle? Well, it uses this really beautiful, kind of counterintuitive strategy. To solve the big problem, you start by perfectly solving all the little tiny pieces first. This strategy has a name: dynamic programming. Now, I know, it sounds super intimidating, but the idea behind it is actually incredibly simple. You take a big, messy problem, and you break it down into the smallest, simplest subproblems you can. Then, you solve each of those little puzzles just one time, and this is the most important part. You store their solutions. You remember the answers so you don't have to solve them again. Probably the best way to get your head around this is with Legos, right? When you're building a complex model, you don't just start grabbing random bricks. First, you build the small, simple sub-assemblies, like the wheel assembly or the little engine block. You build them perfectly. Then, you combine those already solved pieces to create the amazing final model. Dynamic programming is just like that. Okay, so how does this Lego logic actually apply to our line of code? How does it help us find that elegant 5-step path we saw earlier? Well, let's watch the compiler build the optimal solution from the ground up. The very first thing the compiler does is get organized. It doesn't see our code as a flat line of text. It sees it as a structure, a hierarchy, which we call an expression tree. This tree is basically its map of the entire problem. And here it is. This tree shows the relationships perfectly. Way up at the top, you've got the addition. But to do that, you first need the results of 2 other things, the subtraction on the left and the multiplication on the right. This is the blueprint the compiler's going to use. And now for the dynamic programming magic. The strategy is to give every single operation a cost. Think of it like a score in a game. Lower is better. And here's the key. It starts calculating the score not from the top of the problem, but from the very bottom, from the leaves of the tree. So we start at the absolute bottom. To do anything at all, we have to load a value like A or B into what's called a register. It's like the computer's temporary scratchpad. We'll just say that this simple action has a cost of 1. Okay, now we move 1 step up the tree. To figure out A minus B, we need to do 2 of those cost 1 actions. So the total cost for the small piece of the puzzle is 2. We've just solved our first little subproblem. And we do the exact same thing on the other side of the tree. Getting C or D into a register also has a cost of 1 each. Simple enough. And if we follow that same logic, the cost to calculate C times D is also 2. And just like that, by working from the bottom up, we've solved our 2 main subproblems, and we know exactly what they cost. We've built our first 2 Lego pieces. All right, now for the final piece. We get to the top of the tree. To combine our 2 solved pieces, a minus B and C times D, we just need to add them. The algorithm explores the options and figures out that the absolute minimum cost to do the whole thing is 4.
That number represents the best score it could possibly find.
So here's the really cool part. The hard work, it's already done. Because it built this cost map from the bottom up, the compiler now knows the cheapest way to get to any point in the tree. To find the overall best solution, it just has to trace the path of the lowest scores back down from the top. And that path, that sequence of lowest cost steps it just found, that translates directly into the elegant optimal machine code we were looking for from the very beginning. There's no guesswork. It's just following the best score. Okay, let's zoom out for a second, because this idea is so much bigger than just making code run faster. It's really a powerful way to think about any kind of complex problem. This core idea of solving small, perfect pieces to build a large, optimal solution, that's like a mental superpower you can apply to almost any challenge you run into. It's about finding the fundamental building blocks, getting them right, and then putting them together to create something amazing. And once you start looking for it, you see this logic everywhere. In project planning, you nail the small tasks to make sure the final project is solid. When you're learning an instrument, you perfect the scales and chords before you combine them into a beautiful song. Even with your finances, making small, optimal choices is what compounds into long-term success. It's that same bottom-up logic. You know, what makes this all so fascinating is that in a purely theoretical world, the problem of generating perfectly optimal code is what they call undecidable. It's considered impossibly hard. But as the Dragon Book explains, we use these practical, elegant strategies like dynamic programming to find fantastic, incredibly efficient solutions for the real-world problems that actually matter. It's just a beautiful triumph of practical wisdom. And that kind of leaves us with one final thought. As you go through your day, just look at the complex systems around you, in nature, at your job, in how you learn things, and just ask yourself, what here might be hiding an elegant, simple solution, just waiting to be found by breaking it down into its smallest, most perfect pieces?